Okay, a little bit more about sequences. Just to review, we have the sequence of odd numbers, 1, 3, 5, so on and so forth. The sequence of squares, 1, 4, 9, 16, and so forth. And then this relationship between them that says that if we add the first two odd numbers, 1 plus 3, we get the second square, 4, which is 2 squared. If we add the first three odd numbers, we get the third square, which is 9. If we add the first 4 odd numbers, we get the fourth square, which is 16. So the sequence of squares and the sequence of odd numbers are related in a very nice way. Now, what's interesting is when you look at this book of squares written by the mathematician Fibonacci in the year 1225, everything's written in paragraph form. Fibonacci does not have the notation like we have today to write this relationship this way. He has to write it in words in paragraph form. In 1225, there was no equal sign. The equal sign isn't invented until about 300 years later. So Fibonacci didn't have the notation that we have that really simplifies things for us. Now I want to just point out here that these are all numbers and operation symbols like addition and the equal sign. We can take this a little bit further and generalize our work with sequences this way. We could say, for instance, that this sequence let's represent with the letter A, and then we'll use subscripts to tell us what number, what position in the sequence we are. So if I say this sequence is represented with the letter A sub 1 is going to be the first term, A sub 2 the second term, A sub 3 the third term, A sub 4 would be the fourth term, so on and so forth. Let's say this sequence right here will represent with the letter B, and I'll call this B1, B2, B3. So I have different letters for different sequences, but the first term is always represented with the subscript 1, second term with the subscript 2, third term with the subscript 3. So by using variables like this, we can generalize our work with sequences a little bit more. So let's just go on out here and say, I wonder what the nth term would look like. B sub n, meaning any term of the sequence. Well, when I look back here, I see B sub 1 is 1, B sub 2 is 4, which is 2 squared, B sub 3 is 9, which is 3 squared, B sub 4, the fourth term, would be 16, which is 4 squared, so it must make sense that B sub n then would be n squared. So now I've got a way to write any term in the sequence of squares. I say if B sub n is the nth term in the sequence of squares, it must be equal to n squared. How about the sequence of odd numbers? A sub 1, A sub 2, A sub 3. Let's go out here. We'll go 3 more. Or we'll go on and so forth and say, what is the nth term, any term in this sequence? Now, I'll just show you what it is, and then let's see if it makes sense to you. I'm going to tell you that the nth term in this sequence is 2n minus 1. Now, does that work, 2n minus 1? Well, when n is 1, 2 times 1 is 2, minus 1 is 1. When n is 2, 2 times 2 is 4, minus 1 is 3. When n is equal to 3, 3 times 2 is 6, minus 1 is 5. So you see that this expression for the nth term in the sequence of squares works pretty well. So here I'm generalizing my work with sequences a little bit more. How about this relationship right here? Can I generalize that also? Well, let's take a look. If I want to add, let's say, the first n terms in the sequence of odd numbers, it would look like this. 1 plus 3 plus 5 plus dot 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 plus the nth term, which is 2n minus 1. And if I add the first 3 terms, I get the third square. If I add the first 4 terms, I get the fourth square. If I add the first 5 terms, I'll get the fifth square. If I add the first n terms, I'll get n squared. So there's a way to write this complete relationship that Fibonacci talked about for any line that you want to go to, whether I want to go down 5 lines, 6 lines, 7 lines, whatever. Now I'm just going to show you, for those people maybe going on to statistics and classes like that, We even have notation that generalizes this because these type of things come up a lot in statistics, and we write it this way. A big capital Greek sigma standing for sum, the sum from k equal 1 up to n of 2k minus 1 is equal to n squared. There's even a more shorthand way to write this relationship. So this stands for the sum of all of these things from k equal 1 up to n, including all the integers in between. So when k is equal to 1, I get 2 times 1 minus 1, which is 1. When k is equal to 2, 2 times 2, which is 4, minus 1 is 3. When k is equal to 3, 2 times 3 is 6, minus 1 is 5. So I'm just going down this sum right here till I get to the last one, which would be what I get when I substitute n for k, to n minus 1, and I know that that comes out to be n squared because what Fibonacci showed us in his book. So the first thing is to sort of notice this relationship. Fibonacci noticed it in the year 1225, but he could only write the relationship in words. Here we are this year, we have all these symbols that we can write it out with, and it makes our work very nice. Now, if we want to generalize our work with sequences even more, we can introduce variables and subscripts and have a nice way to find general terms for our sequences, and then we can go even farther and write these relationships using variables also.